So from the roots of that quadratic equation, we come to this, that sigma impact will be equal to WL upon E plus under root of WL upon E square plus 2AL upon E into WH divided by AL upon E. Right. So I am only taking the positive root, negative root I am just neglected. So if I take W by A common, if I divide this with this AL upon E, so WL upon E divided by AL upon E, left with W upon A, and I take W upon A common, then it is 1 plus under root 1 square is 1 plus 2H AE upon WL. Right. If you solve this, the answer would be this. Right. 2H into AE divided by WL. So if I write from here that this WL upon AE, this is WL upon AE, this we know as delta static, and this W upon A is known as sigma static. So we can write from here that the impact stress will be equal to sigma static into 1 plus under root of 1 plus 2H upon delta static. Right. So this is the formula which we derived and which we already used, and this bracket term is known as your impact factor, and you know that the minimum value of impact factor is 2 and the impact factor will always be more than 2. So the impact stress is more dangerous than the static stress. Now if you see the two equations which we have the two equations, that is sigma static, which is equal to W upon A, and sigma impact, which is equal to this formula. Just forget about this formula. This is sigma impact and this is sigma static. So if I write that sigma static is equal to load per unit area, then the sigma static is a function of, if you write that sigma static is a function of load and area only. Right. If load is constant, area is constant, then the stress developed during the static loading will be constant. Right. It will not change. So you can say that the static stress is independent of length of the bar and material of the bar. Right. What do we mean by material of the bar? The impact, the static stress which is developed inside a bar is not a function of the material properties like its yield strength, its ultimate strength, or your Young's modulus of elasticity, you can say. So the static stress is independent of this length and the material, right? But if you see from here, the impact stress is a function of load, area, this height h, Young's modulus of elasticity, and this length. Right. It is a function of these 5 terms, that is load or length and height from which this impact load is falling, or this Young's modulus of elasticity, and this area of the body or area of the bar. So it is a function of this. If you see from here, if you clearly see that, I can say that the impact stress is inversely proportional to the length of the bar. That length of the bar, the impact stress developed in that bar is inversely proportional to its length. So we can say if all the other thing is constant, that is load is constant, area of a bar we make constant, height is constant, Young's modulus, or you can say material is fixed, then the impact stress is a function of length and it is inversely proportional to the length. Now we want that in any condition our system or our that bar will not fail. So we are trying to minimize the impact stress in all the possible conditions, right? We want that the stress developed inside any system will be as minimum as possible, so that that system or that bar will not fail under its functionality, under the application of external loads. We don't want to fail that body, right? So in case of the impact stress, we can say if I increase the length of the bar, if I increase this length of the bar, this complete quantity will decrease because it is inversely proportional. So that's why during the impact loading, if you increase the length of the bar, then the impact stress which is developed inside the body will be reduced, and that bar will be in the safe condition or in the safe zone, and it will not fail during its functionality. That is the reason the nut or bolt, that bolt we have, the length of the bolt is long, the length of the bolt is large to make that bolt safe under the impact loading. You know that we are using the bolt, and somehow if this bolt is under the impact loading, so if you make the length of that bolt is very less, then that bolt will fail. So that's why we are making the length of the bolt as long as possible, right? So this is your impact loading, and this is the first type of your dynamic loads under the head of your with respect to time classification of loads. The second is your fatigue load, right? Second type is our fatigue load. Fatigue loads are those loads whose magnitude or direction or both can change with respect to time, right? If I already studied that force is a vector quantity, and if you want to change the force, there are two things. Either you can change the magnitude, or you can change the direction, or you can change the both. Then you can say that yes, the force is changing or the vector is changing, right? So in dynamic load, we want that dynamic loads means whose force is changing with respect to time. So fatigue loads are those loads whose either magnitude can change or direction can change, or both magnitude and direction can change with respect to time, and these loads are repeatedly applied with respect to times. We are continuously applied these loads on the body. Suppose this is a bar. So if I applied a continuous fatigue load, means tensile, compressive, tensile, compressive. So if I do this type of loading, that is first I am applying load in the outward direction, then in the inward direction, and if I change the magnitude, so I can say that in this condition both the magnitude and direction of the force is changing, right? Initially the force is tensile, then I change the nature of the force as compression, so the direction changes. If I pull this body with 10 kilonewton and if I compress this body with 8 kilonewton, so I can say that the magnitude is also changing. So this type of loading in which the magnitude or direction or both magnitude and direction can change, and you apply these loads in a cycle, repeatedly you are applying, so that type of loads is known as fatigue load. And you know that we will study it also in your machine design, that fatigue load is the most important in our study, because all the ductile materials or all the materials you can say will fail under fatigue loading, right? They will fail easily under fatigue loading. If you see that, if I can say that if I want to break this marker, so if I elongate it or if I applied a tensile load, then after some point this marker will break. But if I applied a fatigue load on this marker, suppose in this bending, if I bend in this direction, first of all in this clockwise direction, then anti-clockwise, clockwise, anti-clockwise, and you repeatedly doing this for some time, then this marker will fail, right? And you will surprised to know, and you will feel it when you in your daily life, that under this fatigue loading you applied a very small amount of force with respect to this tensile load, right? If you say that I am applied a 10 kilonewton of force in this direction, tensile load, then this marker will fail. So under the same condition, if you want to fail this marker under fatigue loading, this marker will fail, let us say in 5 Newton, or you can say in 5 kilonewton or 6 kilonewton. So under the fatigue loading, the body will be failing early as comparison to the your static loading, in which the magnitude and direction is same, right? We will discuss it later also. So there are 4 types of fatigue loading. We have 4 types of fatigue loading. The first one is your completely reversed fatigue loading. What do we mean by completely reversed fatigue loading? This is an example of completely reversed fatigue loading, in which suppose this is a load acting on this body, on this bar. Initially, first, plus means tensile in strength of material. You can write here that plus load means tensile load, and minus load means compressive load. This is our sign convention in your strength of material. I am following this sign convention. Plus means tensile load, minus means compressive load. So I am saying, in a completely reversed type of fatigue loading, the magnitude of the load is same, that is P, but the direction is changing. Initially, first the direction is plus, that is tensile load, then compressive, then tensile, then compressive. So in this case, only your direction is changing, direction change, but magnitude remain constant. But your magnitude is constant. So that type of loading is known as your fatigue loading, and or you can say completely reversed fatigue loading, right? Means, so let us say this load is of 10 kilonewton. So I am saying 10 kilonewton tensile, 10 kilonewton compressive, and so on. Only magnitude is remain constant, only direction is changing. So that type of fatigue loading is completely reversed fatigue loading. The second type of fatigue loading is your fluctuating load, fluctuating fatigue load. In fluctuating fatigue load, the direction will be same. Suppose this is a positive, so direction is always positive, always tensile load will be there, but the magnitude is fluctuating from, let us say, 2P to P, right? From, let us say this is 20 and this is 10. So from 20 Newton to 10 Newton, the load magnitude is changing, but direction will remain same. Always the load will be in the tensile nature, but the magnitude is changing, or magnitude is fluctuating. So this type of fatigue loading is known as fluctuating load, in which only magnitude change, direction will remain constant, right? The third type of loading is your alternate loading, alternate fatigue loading, in which both the magnitude and the direction changing, right? Initially, let us say the magnitude and direction is minus P, load is minus P, that is compressive load of P magnitude, and after that the load direction will change from compressive to tensile, and magnitude change from P to P by 2, right? So in this case, both magnitude and direction change. So this type of the fatigue load, in which both magnitude and direction are changing, so that type of load is known as alternating load, right? This is alternating load. Fourth one is your repeated fatigue load. Repeated fatigue load are those fatigue loads which are subjected to, or the bar is subjected to a load whose magnitude is changing from 0 to maximum, right? In this, the magnitude of a force is 0, and the force magnitude will be increasing to maximum, then 0, then up to maximum, then 0, then up to maximum. So in this case, the direction will be same, that is either tensile or compressive, but the magnitude is changing from 0 to maximum. In this case, magnitude is varying from, or changing from, 0 to maximum value. 0 to maximum value. So this type of fatigue loading is known as repeated fatigue loading. So there are 4 different types of fatigue loading we have. You are completely reversed, in which only direction change, fluctuating, only magnitude change, alternating, in which both magnitude and direction change, and repeated fatigue load, in which only magnitude change, but from 0 to maximum. In this case, the magnitude is not changing from 0 to maximum, right? In this case, one magnitude is 0. Suppose this is a bar, so I pull it with 10 Newton, then release the load 0, then again 10 Newton, then release, then Newton, 10 Newton, then release. This is fatigue loading. But this fluctuating load is, suppose this is 20 Newton, then 10 Newton, 20 Newton, then 10 Newton. So this is the difference between your fluctuating and repeated fatigue loads, right? Now we will see that a basic understanding of what do we mean by the endurance and fatigue limit. Endurance limit or fatigue limit. We know that all the materials must have some properties, just like your yield strength or ultimate strength. Those properties are depending upon the material to material or vary from material to material. So endurance strength or the fatigue limit it will give us what will be the failure stress of a material under fatigue loading. If you make one material under fatigue loading, what would be the failure stress? Means at what amount of fatigue loading this member can fail. Suppose we have a mild steel component. So the endurance limit of mild steel means that endurance limit of a mild steel will give us the magnitude or the failure stress of that mild steel, so that we can understand that under the fatigue loading, this mild steel will fail at this limit, right? We always consider because that is the maximum stress, maximum fatigue load, or you can say maximum fatigue stress that body can withstand without failure. We are more concerned about the failure because we don't want during any machine functionality, during any building, if you construct a building, you don't want that this building will collapse. So that's why you need to know that how much amount of load or how much amount of stress these members, these beams, these columns or these various other materials can withstand. So that maximum stress a material can withstand is its property, and under the fatigue loading, that maximum stress a body can withstand without failure is the endurance limit, right? So the endurance limit will be obtained from a test. We will do a test on the different materials, and with the help of this test we are able to plot a SN curve. There is a SN curve. We'll see SN curve in your machine design. SN curve, but the most important thing is the fatigue test is every time the fatigue test is done under the completely reversed condition. This is the important thing. We are only taken the test under completely reversed condition. No other type of fatigue loading is considered during the making of that SN curve, right? So the endurance limit is available with us only for the completely reversed fatigue loading, right? So the endurance limit is the maximum value of completely reversed stress that a material can withstand for infinite number of cycles without failure. Without failure means without any crack initiation, right? So infinite number of cycle means I can do this cycle or I can do this tensile compressive for infinite number of times. In that case also, what would be, this material will not fail. So what is the maximum limit of the stress this body can withstand without failure for an infinite number of cycle? That is known as the endurance limit, and this is for your completely reversed stress only, right? So the SN curve will look like this, right? We'll see it on machine design in detail, but for your understanding, this is how a SN curve will look like, right? So we can say that suppose this is the this is a logarithm graph, S means your shear stress, or sorry, your stress, that is fatigue stress, and N is the number of cycles. So we can say that a body can fail at this point if the stress, suppose this is of mild steel, let us say this is of mild steel. So if the stress is at this level, then this body will fail up after this number of cycles. After this cycle, this much amount of cycle, this body will fail. This is the failure graph, right? If you make the stress at this point, if this is the stress or this is the fatigue, your maximum completely reversed stress, this is a completely reversed stress. So if this amount of stress is developed inside the body, then this body will fail after this much amount of cycle, right? After this much amount of cycle. So after some time we reach a point where if this much amount of stress is applied on the mild steel, then this body will be going for infinite number of cycles. There should not be any failure, right? So this stress is known as endurance limit of mild steel. So you can say this is the maximum stress value this body can withstand without failure for the infinite number of cycles. So this is the meaning of endurance limit.